Okay, well, thank you, everyone. It's a real pleasure to be able to talk to you about this work. Let me start with a 30,000 foot view, and that is with 2 points I'm hoping to get across today. The first one is that crowdsourcing is really an exciting area. I guess I started working in using planning algorithms to control software agents. I think I gave a talk here at this conference in 1996 where we were thinking about that, and that area has developed enormously, and some of the other work people have done have led to Siri and some of the other intelligent agents we use on our phones today. And this is really, crowdsourcing is really another kind of software agent that we're trying to control, and again, planning turns out to be incredibly powerful. So what I'm hoping to do is show you a number of techniques that you guys hold dear already, are very, very powerful in this area. When I say we can save 30 to 85%, I'm not talking about speeding up the computer by that amount, but really by saving human labor, which costs real dollars and is a big deal. So crowdsourcing is really the problem of releasing an open call out onto the internet or some other network to get large numbers of people to come together to solve some sort of problem. And oftentimes the key challenge is in taking small pieces of work that individuals do and putting them together into a giant coherent whole. And so that's crowdsourcing. And let me just give you a couple examples of the wide range of success stories that crowdsourcing has brought us. The first one I'll talk about, it's hard to imagine traveling, planning a trip to some place without looking at either TripAdvisor or Yelp. Together they've got about 140 million reviews and really quite an incredible resource. Another example, I don't really know of a programmer today who doesn't use Stack Overflow, which has a really unique reputation system that moderates the quality of submissions, keeps track of good questions, good answers, and incents people to provide both of those. And then finally, it seems, I think we mostly take Wikipedia for granted, but it's really one of the incredible resources, one of the incredible products, I think, information-wise, that our civilization has produced, an extraordinary resource, again, brought about by crowdsourcing. Another application area or sub-area of crowdsourcing is something called citizen science. So here the idea is trying to enlist large numbers of volunteers to help in a scientific enterprise. Galaxy Zoo is part of the Zoo Universe project, and they've got close to 1 million volunteers doing a variety of tasks. The biggest one, Galaxy Zoo, is analyzing images from the Hubble Space Telescope. And these volunteers, just ordinary housewives and random people, have created a number of scientific discoveries, including new kinds of black holes and different galaxies. Another example, the eBird and Audubon bird count projects allow citizens to upload photographs, identify photographs, and track the precise location and first appearance of birds, which may sound just like a hobby, but in fact it's got big scientific consequences. Because being able to do this accurately and see, the exact times that birds appear in a certain area allows one to track migration shifts and has given us new insight into climate change as these migration patterns have slowly shifted year after year. And as a final example of citizen science, the Fold It project done by my UW colleague Zoran Popovic allows people, it's a game actually, and people play the game using their visual skills that allows them to fold a representation of a protein, and so they can use their visual skills to do this. Turns out scientifically it's very hard, even with the best optimization algorithms, to find the lowest energy state for one of the three-dimensional structures of these biological proteins. And it's just one example. A group of about 15 volunteers working together on this game was able to come up with the three-dimensional structure of a key AIDS protein, and it resulted in a Nature paper last year. And then, as my final example of crowdsourcing, let me talk about labor marketplaces. Not many people have heard of Odesk, but it's really quite huge. About 3 million workers and 35 million hours. That's almost 20,000 full-time employee 8-hour-a-day, 5-day-a-week equivalents. So a pretty darn large labor force growing at 60% a year. It's a phenomenal success. Tiny company is highly profitable. More people are probably familiar with Amazon Mechanical Turk, but we know less about it. So here, employers post micro work, usually small jobs that take less than a minute to accomplish and pay typically a few cents. A few years ago, it was let slip that they've got more than 500,000 workers, but people believe that it's many, many times that. Interesting question is, where are all these workers? Who would actually do these jobs where you only get paid a couple pennies? And surprisingly, a lot of them seem to be in the United States. And as people try to understand that, it seems as if maybe people are doing it only partly for the money, and largely they're doing it, again, for fun. So the motivation is partly economic and partly entertainment, but whatever it is, you can harness people to get very impressive jobs done. So I'm going to use Mechanical Turk as an example, but I think most of the lessons I'm talking about and techniques apply for all of these different systems. So here's a sample job on Mechanical Turk. We've got a photograph, and we're offering to pay somebody 5 cents to write down a descriptive caption of that photograph. Now you might think if you paid people a little bit more, you could get a better description, but it turns out if you raise the price that you're willing to pay people, that tends to decrease latency. So people pick up that job and do it much, much more quickly, but they don't tend to do a higher quality. So if you really do want to get a high quality, very comprehensive image, description of your image, then what should you do? And this, in fact, is the challenge underlying many crowdsourcing problems. So we've got a large number of workers, and they're willing to do small amounts of micro work. The quality varies enormously between these different people. And so the challenge is, how do you actually get a big job done? And the answer people have turned to is to use a workflow to aggregate the results and ensure quality. So oftentimes jobs will be posted multiple times using redundancy, and then we can check the results between different workers to verify quality. In some sense, what we're doing is creating a virtual organization using unreliable workers to manage other unreliable workers. So here's an example coming back to creating a caption. So I've got here on the left initial artifact. Think of that as an English language description of a picture. I'll use the word artifact from now on because all these techniques are much more general than just captions for images, but it's more concrete to think about it as an English description. So one thing you could do, besides the job I showed you a few minutes ago, is you could show a new worker the image, the description that your first worker came up with, and ask them to come up with an even better description. So I'll call that an improve task. And then we could take both of those two descriptions in the photo and go to one or more other workers and ask them, here are two descriptions of a photo, which one is better? And then we could aggregate these votes and then return the best description, or we could turn this into an iterative process, first suggested by Greg Little in his MIT PhD thesis a few years ago, and go around this loop, creating better and better descriptions each time we go around. And continuing again with an example from Greg's thesis, when he went around this loop the first time, this is the description he came up with the image. And his process basically said, every time we do a vote, I'm going to ask two workers, and if they agree, I'm going to assume that that's the better description. But if they disagree, I'm going to ask a third worker, and then I'll take the majority vote. So after going around this loop 8 times, they came up with that description, which I know I certainly couldn't have written. Incredibly precise and detailed caption, and achieved very, very quickly. Here's another example using the same workflow. He asked workers to try to decipher this. Looks like my handwriting, and I couldn't really make out any words, but again, workers trying to do that transcription, and then every time they go around the loop, people would vote to see whether or not progress is being made. After going around the loop 8 times, they had an almost perfect deciphering. That pink highlighting shows a couple words that were incorrect, but overall, really pretty impressive performance. And all of that comes out of this very simple iterative improvement workflow. But there's some interesting questions about this workflow. So Greg had the policy, again, ask 2 people. If they agree, we'll assume that's the answer for the vote. Otherwise, we'll ask a third and take the majority rule. He went around the loop 8 times. But is that really right? I mean, should you really ask that many votes? And how many times should you go around the loop? Obviously, there's a trade-off, because for all of these jobs, you have to pay people. So the more people you ask to vote, the fewer times you can go around the loop. We've got a kind of a challenging control problem. And the cool news is our planning algorithms let us solve this problem. So taking a step back, here's the outline for the talk. What I want to do is go through 2 case studies, one looking a little bit more deeply at iterative improvement, the other one talking about taxonomy generation, and then I'm going to conclude with a couple slides talking about some future challenges. The work about iterative improvement is done by 2 of my PhD students, Peng Dai and Chris Lin. And I'm almost embarrassed to throw up this diagram, because everybody who's taught or taken an AI class has seen this before. But here we go. Here's how we apply it to crowdsourcing. The kinds of actions our agent can do involve submitting these jobs onto the Mechanical Turk workforce. So we've got an improvement job and a voting job. The other action the agent can take is to return the answer to the boss, at which point that's a terminal state and no more processing goes on. And then the kinds of perception our agent can do is to look at the results of a voting task and try to make sense of that. And again, the overall objective that we want to program our agent to maximize is to come up with the highest quality description at the minimum cost. There's going to be some sort of trade-off there. And we'll see sequential decision-making is crucial for this. So we're going to formulate this as a partially observable Markov decision process where the world state encodes the quality of these artifacts, quality of the descriptions that are being produced. We're maintaining a belief state, a probability distribution over those qualities. We just talked about the actions, and our objective is to maximize this utility function. So again, looking at this in a little bit more detail, no more blocks world. What we're going to be doing, since we've got 2 descriptions, is we're going to model each of those descriptions with a real number between 0 and 1. And the idea is if the quality of a description is 0, what that means is that any worker, no matter how unskilled, is going to be able to improve that description. And if the quality is 1, that means even the most skilled worker, if they try to change it, they're going to make it worse. And any real description is going to be some number between 0 and 1. Obviously, this is an unobservable quantity, but we'll be maintaining a belief about this. Since we've got 2 descriptions, we've got 2 quantity numbers, and that's our state space. So we're going to be thinking about belief states over here. So really, we're maintaining a distribution over each of these qualities. And you can represent that distribution in many different ways. We've tried several. For example, you can model as a beta distribution or discretize it, what have you. And so one of the first questions I want to talk about is how do we deal with sensing operations? And since I've got a crowd here, let me ask people, is this an indigo bunting? Or any bird lovers here? How many people think it's an indigo bunting? How many people think it's not an indigo bunting? You guys are pretty lame this morning. I think that was a vote of 2 to 1. It's actually, I think, a bluebird, so no indigo bunting. But if we post this job out to Mechanical Turk, then how do we make sense of the results? Well, the simplest idea is just to use majority voting, and Ryan Snow showed that for a large number of natural language processing tasks, using just totally untrained Mechanical Turk workers, you could actually exceed the performance of an expert linguist by using simple majority voting with 7 or 8 workers. So that's pretty good, but it turns out we can do much, much better than that. So what we want to use instead is a probabilistic model where we weight votes by the accuracy of the workers. That's pretty easy. The hard part is figuring out exactly how accurate the workers are. If you can come up with these accuracy models, then in fact you can save enormously over majority voting, save about 50% of the labor required simply by weighting the votes appropriately. But again, we can't observe the accuracy. So one way of coming up with accuracy numbers is to insert some problems where we know the answer, these gold standard problems. And that's a technique that's widely used in industry. The problem is that the Mechanical Turk workers know that, and they tend to post on forums the answer to all these gold standard questions, and then they write bots that look at a question. If it's one of the gold standard questions in the database, they answer it correctly. Otherwise, they answer it randomly. And so that doesn't work so well. So what we use instead is an expectation maximization algorithm to automatically do unsupervised learning of worker accuracies. And the math is a little bit complicated in terms of this graphical model, but the intuitions are really very simple. So the first intuition is if somebody disagrees with the majority much of the time, then they're probably a low-skilled worker or a spammer. On the other hand, if somebody agrees with the majority much of the time, then they're probably a good worker. And furthermore, as we identify good workers, we can weight them higher, we trust them more, and so somebody who agrees with the other good workers is probably a great worker. And so with sort of this iterative expectation maximization algorithm, we can track over time the quality of all the workers in the labor pool. Okay, so let me come to action model now. And there's really two actions. First action is an improve action. So we've got some sort of probability distribution over our artifact, our description, and now we ask a worker to improve it. Well, based on the skill of the worker, when they create the new artifact, we're going to have a new probability distribution. Hopefully it's going to be a little bit better, especially if it wasn't a good artifact to begin with. But we can basically model this kind of transition diagram. So that's what an improve action looks like. And now if we've got a vote action, then we're showing a worker these two artifacts. Internally, we're showing them the actual descriptions. All we know about them, really, all the computer can manage is this distribution over their likely qualities. And if we show it to a worker and the worker comes back and says, well, it looks to me like artifact 1 is better, then what we do is just update our probability distributions using this Bayesian update. So artifact 1, the distribution shifts a little bit to the right. Artifact 2 shifts a little bit to the left. And again, the amount of the shift is going to be a function of how accurate we believe that worker to be. Okay, so coming back to the partially observable MDP, again, so we've got the quality of the artifacts, the belief space, these two actions, and we're trying to maximize this reward. So we're assuming the reward is going to be a monotonic function that's increasing on the quality of the artifact, and the user has to specify that using utility elicitation methods, minus the cost of all of the jobs that we're submitting to Mechanical Turk. So this is actually a reasonably challenging POMDP to solve. Even though there's only 2 state variables in the world state, they're both continuous variables. And POMDPs obviously involve distributions over those, so it's kind of a nasty state space, and there hasn't been all that much work on solving POMDPs over continuous state variables. We looked at a number of different algorithms, and I'm a little bit embarrassed, even though this is a planning conference, the focus of my talk is not going to be the algorithms we use to solve the POMDP, but we tried UCT on a discretized space. In the end, it turns out what worked for us was a simple look-ahead search modeling these distributions as beta, and we only had to look ahead, say, four actions deep to get quite good plans. I'm going to, rather than going into the details of how these solving algorithms work, I'm just going to try to give you a flavor of what happens as we solve the POMDP. So here you can see as input, we've got our belief about the initial artifact, And the first question the system has to answer is, well, maybe we're done already. Maybe we can just return that to the boss. If the answer is no, then we're going to generate an improvement job and send that out to the workforce. And that's going to come back. We'll have a distribution of our prior over this new artifact. And now the question is, are we confident enough in the quality of our artifact? If not, then what we want to do is we want to create a ballot job, send that out for a vote on Mechanical Turk, and then based on the results of the vote, that allows us to update our belief about the quality. And now we're back to the question, are we confident enough about the quality? If not, we're going to create another ballot job, send it off to Mechanical Turk. Now we're confident enough about the quality of our new artifact, so we can go down and compare these two artifacts, choose the one that's better, and go around the loop again. And this time we decide actually the result is good enough, and so we return that back to the boss. So that's sort of the behavior of the POMDP algorithm. And so it turns out that using this POMDP and comparing it to the hand-coded policy that Greg Little used in his PhD thesis, for the same amount of money, we get much, much higher quality descriptions. Or if you fix the quality of the description, then we can generate the same quality descriptions for about 30% less money paid to Mechanical Turk workers. A more interesting question, though, is how does our system allocate the behavior? So again, the hand-coded policy, again, asks two workers. If they agree, it returns the answer. If they disagree, it asks a third to break the tie. And so on average, you can see it uses about 2.5 votes per iteration. Our system, it turns out, does this. When we first thought this, we thought that there was a bug in the POMDP algorithm. It was only after we sat down and scratched our heads a little bit, we realized that, in fact, it's actually being quite sneaky and smart. So initially, the artifact is not very good, or so the POMDP reasons. And so it's pretty easy for a worker to improve it. So our algorithm just assumes that the new one is better. It doesn't do any voting at all. And then after iteration 4 or so, it starts asking voters, because at this point it gets harder and harder for workers to improve it, and there's a bigger chance that they're actually making it worse. And as a result, as it becomes hard to distinguish between the quality of the new and the original description, it can use as many as 7 votes to do that disambiguation. And as a result, also, it allows the POMDP to go around the loop more times and make the system better. So this sort of smart allocation of effort is really what the planning algorithm buys us. Okay, so this POMDP control allows us to have higher quality to reduce labor costs, and then the key thing is being very careful about how we maintain belief states about this uncertain world and taking care when we model sensory actions. That we also need to do expectation maximization to learn these accuracy models for our workers. And we'll see the same lesson playing out in this next case study. So here I'm going to talk about taxonomy generation. And let me start with the work of another UW PhD student, Lydia Chilton, who you'll notice from this photo is a Star Trek fan. So she originally thought of this task of taxonomy generation because there's so much content on the internet which is hard to organize. So what she's trying to do is take input like photographs and generate a taxonomy over those images. And then place all of the photographs at different points, appropriate points in the taxonomy. So here we've got all the tiger pictures, here we've got the pictures of workers, and all of the tags and the hierarchical structure over those tags were generated by her algorithm using crowdsourced labor. Same algorithm works for question and answer, for answers to questions posed on Quora or some other QA site. So there's usually many, many answers to these questions, and it's hard to browse through and figure out which of the answers are going to be most interesting to you. Her system uses crowd labor to generate a taxonomy to organize this, allows for much easier browsing. Now, it turns out that taxonomy generation is actually a really hard problem. when you try to crowdsource it, because a good taxonomy requires a global perspective of all of the data, and yet each of the workers sees only a tiny, tiny fraction of the data, maybe only one image or one answer in response to a Quora post. So how the heck can you create this global perspective? Well, Lydia tried a number of different algorithms, and the first one, unsurprisingly, was iterative improvement. So here, she showed the workers a set of the tips. These are answers on Quora. And on the left-hand side, I'm not sure if you can see it, is sort of a wiki-style representation of the taxonomy. And the workers were asked to improve the taxonomy or to locate where a particular tip was in the hierarchy. And she futzed and tried to get this workflow to work, but fundamentally it just didn't work. And the problem was that the hierarchy grew reasonably quickly and became overwhelming to these workers who really didn't have the patience to work for more than a few seconds or a minute. And furthermore, the workers were confused. They didn't really know exactly how they should make progress. So the takeaway lessons were really need to break the task down into smaller steps and provide more direction to the workers. The second thing she tried was to create a workflow that involved category comparison. So here, she would show, and again, I'm not sure if you can see on the left-hand side, she would show a category tag from the hierarchy, and on the right over there, we've got a number of other category tags, and we're supposed to basically figure out whether or not this tag is, more general than, or a subset of, or equivalent to the first tag. And the hope was by coming up with these inequality ratings, we could then organize things into a hierarchy as well as recognize duplicates. And unfortunately, again, it just didn't work at all. And the problem was, without specific context, it was very hard for the workers to make sense of the judgment and really understand whether one tag was more general than another, whether they meant the same thing. And so the takeaway lesson was workers really aren't very good at comparing these abstractions. They're pretty good when you give them concrete tasks and concrete tips or photos to label, but they can't handle these abstract tasks. So the algorithm that Lydia came up with had an interesting combination of crowd labor and human labor. So she used the crowd with 3 different kinds of tasks she posed to Mechanical Turk. First one was to take one of these items and generate possible category names. The second one, sort of a brainstorming phase. The second one was to go through and select the best categories. So this sort of filtered out duplications and vague terms. And then the third one was to actually place the data into these best categories. And then after that, she basically used a computer algorithm to do sort of the global taxonomy generation from that. Let me run through this process with a simple toy example. Suppose we wanted to come up with a taxonomy over 100 random colors. What her algorithm would do first is it actually samples the data into an initial set to keep things manageable in size. And then for each color, she posts one of these generate jobs on Mechanical Turk, asking people to come up with a category tag for that color. And as a result, we get an initial set of category names based on what people say. And then in the second step, she would go through, and for each color, again, she would suggest a bunch of category names that people had come up with and ask people to whittle that down into a subset. And so this is a way of getting rid of spam as well as these vague category names. And then in the final step, she would have people go through again and actually label where that color fits into the hierarchy. Notice again, she's trying to make sure that it takes the same amount of effort to label something as fitting as not fitting to avoid biasing the workers. And so here, coming out of this, we've got a set of votes showing which categories are applicable. And this gives us clues into category membership. And then the final step is a machine step. So basically using the statistics she's gotten from that labeling, she's able to figure out which categories, based on their extent really, which categories are subsets of other categories, and which categories are duplications, and so she can build a hierarchy. So out of this she is sort of deducing the parent-child relationships and getting rid of duplicates. And then the final step is to recurse. So we've generated that small taxonomy. Now we go through with all the rest of the data and try to place that data inside this taxonomy. And typically what happens is that some elements don't actually fit anywhere because the original sample wasn't representative. And so we actually need to go through that loop again, generate some new tags, eliminate duplicates, expand the hierarchy, and continue. But let me ignore that subtlety in the algorithm and just keep on going to the validation. So she published this in Chi a month or two ago, and the results were really quite promising. So on the quality level, it turns out that the quality of the taxonomies that she generated compared quite favorably to the taxonomy she generated by hiring experts from the information school and asking them to come up with a taxonomy. And so on the graph here, you're looking at inter-annotator agreement. You can see that people agreed with the algorithm almost as much as they agreed with each other. So that was pretty good. The other thing she evaluated was cost. And here, unfortunately, the results weren't so good. So the crowd algorithm took 2 to 3 times as much effort, as much money. It took quite a bit longer time, but you had to pay the crowd workers less than the experts. So it cost 2 or 3 times as much. So this was very disappointing to Lydia, but I hope you can imagine it was actually delightful to me because it meant that now is a chance for us to put some decision theoretic control in there and see whether we can use a planning algorithm to make things work better. Another PhD student at UW, Jonathan Bragg, has been looking at this problem. And the first question is, why exactly is Cascade so expensive? Where's all that money going? Well, it's not really the generate task, because you don't call that too many times. And it's not the select best task, because we don't need to do that very many times. It's really in this categorize task, because we have to call those, we have many, many instances of these categorized tasks. So Jonathan focused on that to start. And the first question is, well, do we really need all of these questions? And you know, as you might guess, the answer is no. If we're using labor more intelligently, we can probably get by with fewer questions. The more interesting point, though, is we can do better than that. It's really, what's the best order in which to ask these questions? And by choosing a smart order, we can really improve things a lot. So Jonathan came up with a POMDP model. It's a little bit more complicated than one we looked at before. So the world state is really a taxonomy plus the labels applying to an item, the current item that we're looking at any one time. So I've tried to use these colors to suggest probability distributions over the possibly applicable labels for that photograph. And the belief state is going to be then a distribution over these taxonomies and the probabilities for each of the labels, how the labels might, which labels are more likely to apply. I've drawn it out kind of graphically here. In fact, we use a compact encoding of this, and that's sort of the key of Jonathan's contribution. But this sort of gives you a sense of what's going on inside the algorithm. And the thing that's really challenging is, of course, we don't have this to begin with. We don't have the taxonomy. We're learning the taxonomy as the system executes with all the crowd labor. So we sort of initially start out with this uniform distribution, assuming the taxonomy is completely flat. And as we get more and more data, as we're labeling more and more items, we start building up our model of the taxonomy, and we can be more efficient as we go. So in the initial items, we're actually going to do something very similar to what Lydia's algorithm did. But after we've seen, say, 100 items, we can be much more efficient. But this is a really complicated belief state, and we didn't really think that the current POMDP algorithms even though they've improved enormously, were going to work for us. So Jonathan built a simple POM-DP algorithm that's specific to this system. And here's how it works. As we see a new data item, a new photograph that we need to taxonomize, what the system does is it considers all the labels it could ask about, and it asks about the label with a maximum value of information, calculates how much information it's going to get for each of these queries. Asks the maximum value of information, so it's doing a one-step look-ahead greedy search on value of information. And then when we get the answer back from a worker, we do a probabilistic inference to update a number of things. We update our posterior probabilities for all of the labels, not just the label we asked about, but all the other labels. And Jonathan's explored a number of different graphical models to represent this. On the left, you've got a naive Bayes representation, which works surprisingly well. And then more complicated algorithms that represent the belief distribution of the taxonomy more accurately, but take a more computational time to do these updates. So we update the posterior distributions. Again, the key thing here is we can ask about one label, but the answer that a worker gives us about that one label tells us a lot about all of the other labels as well. So we also update the co-occurrence model for labels. And then finally, we also update our model of worker accuracy at each step through this process. And here's the results. So this is the performance of the POM-DP model. I've got the F-score in terms of sort of a harmonic mean of the precision and recall in terms of how many of the labels are we accurately returning. And you can't really see, there's the cascade algorithm off on the far right. And the conclusion is, by using this POM-DP model, even though it's a simple model, we're able to get the same performance as Lydia's algorithm with only 13% as many voting jobs. So that's really a pretty exciting improvement. And as a result, we now believe that we can generate these taxonomies much cheaper than experts, and again, at a similar quality. Okay, so again, hitting these lessons. POM-DPs are great, and they really allow us to get much better accuracy here. And I've shown it working on iterative improvement on taxonomy generation. The same approach has been applied to a few other problems. So here is some work done by Eric Horvitz's group at Microsoft Research. And they applied it to the citizen science task. Again, these workers are trying to classify images of galaxies from the Hubble Space Telescope. And there's a big database, as I said. Their approach is actually very similar to ours in the sense of they're trying to figure out which question to ask which worker that's going to maximize the value of information. They also throw in a machine learning classifier as another worker, obviously a worker they don't have to pay, and then they try to come up with the best plan. In their case, actually the best plans involve substantial look-ahead. So they use a Monte Carlo algorithm like UCT to generate their plans, doing a much deeper look-ahead than we did. But the lesson's the same. They show that their POM-DP approach saves huge amounts of labor. In particular, they could get the same accuracy that the Galaxy Zoo folks got using only 15% of the votes, and their most accurate model topped out at about 54% of the workers. So a big savings. And again, even though you're not paying these volunteers, you want to give them interesting tasks, and you want to get the most from the effort that they're willing to donate to science. Okay, so what I'd like to do now is sort of close the talk with a couple challenges. These are things I don't really know how to solve yet. And so I hope you guys will perk up your ears, especially because we need extra help. So I think you've gotten the idea that I'm really excited about POM-DPs. I really think that this makes a huge difference. Crowdsourcing is a really hot topic. Many conferences, whether it's the HCI conferences or AAAI, have lots of crowdsourcing papers. In fact, there's a whole new conference, HComp, for human computation, which is having its first instance this fall. So it's a big burgeoning area, and I think AI and planning really should be prominent in that. So I went to my colleague, Rob Miller, who's one of the leaders in the area, a faculty member at MIT, and I said, you know, why aren't you using these methods? They're so awesome. And his answer was, really, they're too heavyweight. And it's just a lot of effort to get his graduate students up to the point where they can, you know, understand reinforcement learning and POM-DPs. And so I said, okay, well, that's fantastic. What we need to do is bottle up our system as a toolkit and make that available so that people can take whatever new crowdsourcing job they want to do and make it readily available. That seemed like a great task. But it's actually not that easy. So how exactly are people, when I go to Rob or one of his graduate students, how do I tell him that he should model his crowdsourcing task? I know the answer you're going to suggest, and that's to use PPDDL, right? No, I don't think so. They don't like that. They don't understand that. They don't want to think about transition models. In fact, no one really knows what these transition functions are. I didn't go into the details. We use reinforcement learning to try to pick them up, and you really have to have the model be independent of that. You can't ask them to specify transition functions. In fact, it's worse than that. They don't really even want to think about the state space. So when we encoded both of those POM-DP models, the first one, I used that strange representation of these qualities between 0 and 1. Where did that come from? That's not something that they're going to be able to sort of easily know. Of course, that's what I should use. Or in the taxonomy generation, where I had these probability distributions over taxonomies and label co-occurrence and so on. If they have to specify things at that level of detail, we're not going to get our methods out there. So really what they're comfortable doing is specifying a policy. So they're happy to write down in some sort of procedural language a suboptimal policy, and I think we can get them to specify a utility function as well using preference elicitation methods. And given those two things, what we need to do is we need to have a system that can automatically figure out how to optimize that policy. And to do that, it's going to have to figure out what the state space is by itself. It's going to have to, in some sense, induce the state space, and it should presumably be something which is isomorphic to the program histories that their procedure is generating. But of course, it's got to be more compact than that. So how can we do that? And of course, we also need to learn the transition functions and observation functions. So the solution, I think, and again, we don't have this working at a point where other people can use it, is to think about something that's like probabilistic HTMs. So where people can specify that procedure is a partially ordered set of tasks. We can do recursive expansion. And as an example, suppose we take the task of trying to translate something between language A, English and Italian. Well, one workflow we could come up with would be to ask two humans to do the translation and then have a choose task, which might be one or more voters. A POM-DP would decide the right number of voters to decide which of those translations is better. But another approach would be to use a machine learning translation algorithm to translate between A and B, and then have a native speaker in Italian do a proofreading step to try to make that translation more fluent. And that proofreading step could be expanded in something that is a find, fix, verify workflow. It's actually a lot like iterative improvement. Or yet another workflow could be to translate into some intermediate language and then translate from that language to Italian. And so our student Chris Lynn has done some work that allows us to think about how to actually automatically switch between these workflows and figure out what the right choices are. But thinking about this hierarchical decomposition is kind of challenging. And the basic idea that Chris is pushing on is trying to compile these things into a hierarchy of abstract machines, a model that Ron Parr and Stuart Russell came up with a number of years ago. And again, that can compile us into a POM-DP. And so we have a limited compiler built, but it's not at all clear that this representation is going to be something that people can use. And so other approaches are well worth looking at too. There's a lot of related work here. The stuff that's most close is actually some of the work done by Alan Fern's group on adaptive programs. Very similar objective to ours. They assume full observability. One could probably extend that. Probably the biggest difference is their system requires a programmer to specify the state variables, whereas Chris's approach is trying to automatically induce state variables based on these sort of primitive design templates that an expert has encoded that were the base of the base workflows in that last diagram. Another challenge is, in all of the models that I've talked about so far, and even the work that Eric Horvitz and other people have done, the model is almost always one that allows workers to choose the jobs to perform. And I love free choice, but I think that this is really largely an outgrowth of the underlying models inside the Amazon Mechanical Turk labor force, which has many, many assumptions that I think are faulty, in particular anonymity of workers and poor reputation system and so on. What if an employer could assign the jobs to the best worker? In fact, we know that Microsoft and Google and a number of other companies have large internal crowdsourcing efforts. At Google, they use their internal crowdsourcing labor force to analyze street view diagrams to update the Google Map database. They also use it to update the knowledge graph and to do search relevance distinctions. And different workers working on these different problems have different amounts of training. And so really what they'd like to do is be able to allocate the jobs to the people who have the right training for or the best skills to deal with these individual tasks. But it's not quite clear how to do that. Similarly, in task routing, in citizen science, what we'd like to do is maybe give tasks initially to novice workers, but then if novices are disagreeing and we're finding hard tasks, then we'd like to move them to somebody who we know is more skilled. We don't want to overload the skilled worker with the easy cases. How can we do that automatically? Well, you can formulate this process as having a set of jobs, each one with a difficulty, having a set of workers, each one with a capacity, the maximum number of jobs that they can do, and a skill level. And we'll assume that the errors are independent for these workers. So the objective is to minimize the overall error with respect to a fixed budget, so we can't ask every worker to do every job. Now, if you know the difficulty and the skill level, then it seems like this just maps into a knapsack problem. Basically, what we're trying to do is pack the jobs with the best workers, the biggest workers, subject to the capacity constraints. But that's not the situation we really deal with. In real life, we don't know these quantities. So if we don't know the difficulty of a problem, and suppose we do know what the skill levels are, then assigning an unknown problem to a worker is kind of like pulling the arm of a multi-armed bandit. Okay? And once we find a hard problem where workers are disagreeing, after we've pulled that problem a number of times, then we could more adequately assign the expert workers. Similarly, if we know the skill level but we don't know the difficulty of the problems, then assigning a worker is kind of like pulling the arm of a multi-armed bandit. And so coming up with the optimal way of solving this worker problem, sort of scheduling problem, in the case where we've got unobserved quantities, is really involves solving this exploration-exploitation trade-off as you're trying to figure out how hard is the problem, how good are the workers, while actually doing the assignment. And it's not at all clear what the best policy is. So I think this is a great problem for people to think about. Okay, so in conclusion, crowdsourcing, really hot area, and I think it is really ripe for some of the techniques from this community, and I hope that all of you will consider working on this, because AI planning and POMDPs in particular have enormous potential to speed up these workflows and get real work done. There's many, many open questions, so please have at it. And let me end by thanking my many collaborators, especially Mossam, with whom I've done pretty much all of this work, as well as various funding agents that have made the work possible. Thanks so much.